I'm hoping that a lot of this is going to be review. Okay, you should have done probability in geometry class somewhat. You maybe even did some of it in middle school, but we're going to make it a little more intense here in stats honors, just so we're clear, and we're going to start with definitions like usual to get us all on the same page, so we're all sort of speaking the same language. Okay, so this 4-1 sample spaces and probability, we're going to do some very basic probabilities, and we're going to introduce the idea of how to calculate, determine a sample space. Okay? So the first thing, we have to define what probability is, and that is the chance of an event occurring. And when we say a chance, we're talking about it in terms of decimals, percents, or fractions. Secondly, a probability experiment, an activity that by chance results in an outcome. That's not right. Let me fix that. Okay, so sorry about that. Chance process that leads to well-defined results called outcomes. That's how we're going to use the definition of a probability experiment. Basically, all it really means is there's theoretical probability, which how it should work by the numbers. And then there's often called experimental probability. You conduct the experiment and determine probability based off of your experiment. Okay, that's really the difference. So for example, if you wanted to see how many times when flipping a coin you would get heads out of 100, we know what it should be in theory, but if you actually flip a coin 100 times and see how many heads you get, that would be the experimental probability. And the process of flipping the coin, that's the experiment. Okay. Outcome. The result of a single trial of a probability experiment. So, one flip of the coin, whether you got heads or tails, that is the outcome. Last definition, sample space. The set of all possible outcomes of a probability experiment. And we're going to work on sample space because in order to actually determine probability, we have to know all of the possible outcomes. And that's where we're going to start, is trying to determine that sample space. Let's talk about sample space and try to come up with the sample space for these 5 examples. Okay? So the experiment would be, A would be tossing a coin, so flipping a coin. B would be rolling one die. You know, die is the singular form of dice. Did you know that? Dice is the plural form of die. Answering a true-false question, tossing 2 coins instead of just 1, and rolling 2 dice. So we're going to talk about the sample space and how to find the sample space for each of these. And why this is important is because the number of total possibilities that could exist for each of those things is going to help us determine the probability. So before we can really find the probability of anything, we have to know the sample space and the number of outcomes, possible outcomes in the sample space. So the first one should be pretty straightforward. What are the possible outcomes when you flip a coin?
Heads or tails?
Heads or tails, okay? So those are my possible outcomes. And there are how many of those?
2.
There's 2 outcomes. Okay, so the key here is that the sample space has 2 possible outcomes in it, and that number is going to play a role when we determine probability. How many possibilities are for B, rolling
6.
1 die? 6. What are they?
1, 2, 3, 4, 5, 6.
Correct. Very good, class. Okay, finish them. Do the next 3, since those seem so easy for you. Possibilities. How many possibilities for C? 2. There's 2. True or false. Okay. So tossing 2 coins. Sam asked me a question. Yeah, Sam, ask your question again, please.
I said, you just put
Heads, heads, tails, tails. What else?
Heads, tails.
Heads, tails, tails, heads. Okay, so you're going to have 4 different possibilities. Right? Heads, 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 tails, 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 heads. Now, as we move on to more complicated situations, you're going to want to establish a system to come up with all of them instead of sort of just trying to think about all the combinations. And I started that here. I decided that the first one was going to be heads, and then I would alter the next two. Then I said, okay, that's all. That's all the possibilities when heads comes first. Then for the second one, so now I got to go tails first, and those are my possibilities for those. Okay, so that way I guarantee that I came up with all of them. Question.
C.
For E, rolling 2 dice, how many possibilities are there going to be?
12.
12, 36.
Really? Sure.
Isn't there like a multiplication way to find out?
Is there a multiplication way to find out?
That's what I thought I was always
12 times 12, 144.
So, this is on page 184. Okay?
old, that's just
Yeah, we're not.
If you want to take a picture of the screen, you may also do that. But Bridget, you are correct. There are 36. And because there are 6 possibilities on each coin, you're right. We'll get into the multiplication rule later, but you're right. Because there's 6 possibilities on the first die, 6 possibilities on the second die, there's a grand total of 36 possibilities.
This is on the die.
Yep.
The dice.
Okay?
Dice. So we just sort of.
On the topic of gambling and casinos, one of the other things that we need to be clear on is a deck of cards. Now, hopefully you still play cards. I don't know if teenagers even know what cards are anymore, but like a playing deck of cards. If you were not sure, this is also on page 184. Every standard deck of cards consists of 52 cards. There are 4 suits. These are called suits. The hearts, diamonds, spades, and clubs. Okay. There are 2 sets of colors, reds and blacks. The diamonds and hearts are red. The spades and clubs are black. Every suit has 13 cards, and they list ace as like it's the lowest, but sometimes ace is also the highest when it comes to playing cards, depending on the game that you're playing. And then when you get up here, please do not call these J's, Q's, and K's. These are jacks, queens, and kings. Okay? So this is how every deck of cards looks. And we will spend a lot of time with probability and cards. Okay? So if you need this, you can take a picture of it from the screen. If you want to screenshot it from your book and get a better picture, great. If you know cards, then you're probably in good shape. Okay? We're going to use those a lot as we work through probability. All right. Let's talk about another way to construct our sample space. And we already know the answer to this because we did it and it was simple enough, which is why I want to use it as an example for a tree diagram. Because as you get into more complicated experiments, it's going to be harder to determine if you've found all the possibilities. And the tree diagram is one of the ways to do that. So what we think about, and this kind of gets to what Ashton was talking about, like, are they numbered? Does it happen at the same time? Does one and the other? How do you know which one goes first? When we think about sample space, we think about it sequentially. Like, one thing happens, then another thing happens. And they might be almost simultaneous, but in our minds we need to think of them as separate situations. Okay? So when I flip one coin first, we know that there are 2 possibilities. There's a head and a tail. Okay, and I spread them out like that because this is how I'm going to construct my tree diagram. So that's the first flip, the first toss. Okay, now the second toss for heads, that coin still has 2 possibilities. So from that first head, there are 2 possibilities. So, and the same thing from the tails. From the first tail, there are 2 possibilities. What I do is I split those off that way. So this would be like the first flip here. Okay?
Wait, so we're calling
And then flips, tosses, whatever you want to call it. Okay? And then for the second one, the possibilities that line up. And this is where I come up with my total. Okay? Because, for example, from here I could have a head or a head tail. A tail head or a tail tail. This tree diagram is useful, like I said, when you have more possibilities than just two. But I wanted to use this as a simple one since we already understand how to calculate that. So that's where all my totals come from. And my possibilities come from. This ends up being sample space that we already came up with. We could do it simple enough. But if we had a situation, for example, if we wanted to look at the dice, okay, and I had the 6 possibilities on the left, and then each of those 6 possibilities had 6 possibilities attached to that for the second die. So sometimes creating that tree diagram, it's helpful to see it in order to determine the sample space, okay? You will have to do that in your homework, but I wanted to make sure that I showed it to you so you could kind of see what to expect.
The tree diagram.
Yeah. What? Sometimes tree diagrams are vertical as well instead of horizontal. So you could start with the heads and the tails at the top and work your way down. It doesn't matter. All right. Let's talk about some more definitions as it relates to actual probability. So the event is the set of outcomes. So when you flip the coin, the event is the flipping of the coin. The outcome is what you get. The rolling the die would be the event. The outcome is the number of different possibilities you can get when you roll that die. Where we're going with all this is to formally define probability so that we can calculate it mathematically. A simple event is an event with one outcome. Yes.
Is that from McDonald's?
It's yes.
Why'd they give you that cup?
Yes. A compound event has 2 or more outcomes. Now let's actually define probability. Okay.
Wait, what?
This is also in your book, or you can take a picture of the screen. It's up to you. Probability of event. Number of outcomes in E, the event, whatever that is. That letter E is going to stand for the event. The probability is, and here's what this all means, so you want to write this in. The probability of an event equals the number of outcomes in the event and the total number of outcomes in the sample space. That's what this notation means. Okay.
So we would use
Total number of outcomes in the particular event we're talking about, divided by the total number of possible outcomes in the entire sample space. And this is when we were talking about sample space before. I said we need to know the total number of possibilities. That's what this is. The event that occurs in that experiment, for example, or that particular situation is what's going to go on top, and that's going to determine our probability. It'll be easier when we go through some examples. Okay? So let's start here with some probability rules, and then we'll do the examples after that. Okay? There's lots of things that we need to talk about here. Okay? The probability of something happening, some event occurring, has to be between, inclusively, 0 and 1. Okay? What would the probability, if the probability equaled 0, what would that actually mean?
No chance.
No.
No chance of it happening, right? Okay. So if an event cannot occur, the probability of that event, that notation, equals 0. There's no chance, no way it could ever happen. When we talk about the probability equaling 1, what does that mean?
It's definitely gonna happen.
It's definitely gonna happen. Okay? So when we talk about if an event is certain to occur, definitely gonna happen, the probability of the event equals 1. So everything is in that range, right? It's either never gonna happen, or it's definitely gonna happen, or it's gonna happen part of the time. Okay? And that's why we look at this equation up here. If it's happening part of the time, it's going to be in between 0 and 1. If it always is going to happen, it's going to be 1. If it never is going to happen, it's going to be 0. And then we have everything in between. The sum of all probabilities in a sample space is going to equal 1. What that means is, if I look at all the possible different outcomes in one sample space, if at some point we look at all of the possibilities, it's going to equal 1. So let's think about it this way. If I was flipping 2 coins and I wanted to know the probability of getting 2 heads, that would be one possible outcome, right? There's one way to get that out of 4 total, so it's 1/4. But if I wanted to look at all of them, each one of those outcomes is 1/4. I add them together, I get 1. That's what that really means. The complement of an event. Okay. Did I need to go back? Did I go too fast?
Yes.
Okay, sorry about that. Let's now go on. Complement of an event. The set of all outcomes in the sample space that are not included in the event. Okay, and here's what that means. Let's say I wanted. It's often going to look like this. Let's say, what's the probability of rolling a 5 with 1 die? If I wanted to roll a 5, how many ways can I roll a 5?
1 out of 6.
1 out of 6. Okay, so there's one way to get a 5. 6 ways total. The probability of rolling a 5 is 1 out of 6. 1/6. The complement's going to look something like this. What is the probability of not rolling a 5? Okay. So in other words, we take that event that the not is about and throw it out. Okay. So the complement's going to look like 1 minus the probability of it happening. So in my example, the probability of not rolling a 5 is 1 minus the probability of rolling a 5, which we just determined was 1/6, and 1 minus 1/6 was 5/6. Okay, so that's the complement, and the key word here for complement is the not. Okay.
Hey, why is P now a
Okay, so I'm going to put an example on the board or on the screen. Take a picture of it. Don't write it down, okay? Because it's wordy. Take a picture of this, and then we're going to discuss this. In this problem, we see a survey. 16% of American children said they use flattery to get their parents to buy them things. I think that number is low.
Flatter them?
Flatter to your parents to get them to buy them stuff. If one child is selected at random, find the probability that the child said he or she does not use parental flattery. Okay? So, if 16% say that they use parental flattery, the ones that not are the complement of that. Okay? So how would I do that calculation?
Maybe convert to decimal.
You could convert to a decimal, but I don't need to. Because the complement says 1 minus the probability of the event. Well, the probability of my event is 16%. What is 1 as a percent? 100%. So what is my answer? 84% is the complement. Okay? So yeah, if you went 1 minus 16, that's not going to work. You got to make sure that your units are the same. So in the case of this, if we keep it as a percent, which we would because the problem's written in percent, you have to also convert 1 to a percent. So if 16% said they use flattery, the rest don't. And that's why that may be true. 1 minus, okay, so that's where my 84% is going to come from. Now let's get into some examples. So what I want you to do is try to find the probability, and I want you to do them as fractions. As fractions reduced. I'm going to say this one time. You must always reduce your fractions. It doesn't have to be in the directions. Nobody has to tell you to put it in simplest form. It is understood that fractions always get reduced. That's the last time I'm going to say it. Okay? So make sure on your tests and quizzes and homework that you reduce your fractions all the time. Alright, See if you can figure out these three.
How does fresh?
Look back at your definition, your formula for probability. That might help you try to figure these out. If necessary, you can even look at the page that has the sample space with all the cards on them, since these three examples are talking about a standard ordinary deck, to help you figure out the total possible outcomes for each event. Let's look at the first one to make sure we're on the right track. Okay, how many kings are in a deck? 4. So this is going to be 4 out of how many cards total?
52.
Which reduces to
113.
1 out of 13. Okay, that's how you do the first one. The probability of drawing a king out of a deck is 1 out of 32. And again, just to be sure, drawing means picking a card. Does not mean drawing a picture. Okay? How many red kings are in a deck? 2. So this next one is going to be 2 out of 52 or 1 out of 26. Now, here's where it gets a little more complicated, right? Because there's how many 7s in a deck? 4. How many hearts in a deck? 13. So is it 17 out of 52?
No.
Why not? Because 7 is one of the hearts. So if I count those and I just add them together, I've counted a 7 of hearts twice. So I'm either going to count it in my 7s or I'm either going to count it in my hearts.
19.
So at the end of the day, what it needs to be is 16 out of 52. Okay? Because of that 7 of hearts counting in both the 7 category and the heart category, I can't count it twice. Okay? So now I have to reduce this. 4 out of 13. Okay? So this is when you get into those OR situations. Now that's a compound event. 2 different things going on. Okay? You have to watch for the doubles. And in that case, the 7 of hearts gets counted in the 7 category and the hearts category. So that's why I reduce my number from 17 to 16 because I don't want to count it twice. Okay? Anybody have all 3 of those right? I know a lot of you had the first 2. How many had the first 2 right? Okay. Now the last one was meant to be a little tricky. Okay. Let's look at a few more examples. Yeah. Next examples. Okay, this one's a little trickier. Family has 4 children. Find the probability that the family has 3 boys.
Look at my Z.
Okay? Find the probability that the oldest child is a girl. And then find the probability that they are all girls. So what's important here, and this is where you might use your tree diagram, you have to know how many total possibilities they are for a family with 4 kids. Okay? So we have to know about boys and girls. And so you need to figure out how many total possibilities there are first before you can figure out how many different ways you can come up with these things. So if I were you, you might want to start with a tree diagram here, knowing the first child, second child, and it might be first child is the first one born, second child born, third one born, fourth one born, because for part B, we're looking at the possibilities where the first child is a girl. So you might start with a tree diagram here that's going to have 4 different levels. Then you can determine how many possible outcomes there are. That's a good systematic way to do that. So here's the thing. You can try to create the number of outcomes in your head and write them down and hope that you get them all. And you want to do them in a systematic way so you can guarantee it. The tree diagram will ensure that that happens. So obviously the first child, it's either a boy or a girl. Then the second child is either a boy or a girl. And for each of those, it's a boy or a girl. Okay, and you just have to keep going until you have 4 kids. So I have 1, 2, 3, 4 levels now. So it ends here. And you would have to just kind of keep going on that. So one possibility here is boy, 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 boy. Boy, 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 girl. Boy, boy, girl, boy. So all those possibilities you've got to look at because the order matters. Each level, right? For each level, there's going to be another 2 possibilities until you get to the 4th kid. So what this really looks like here is one possibility right there, one strand. Boy, 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 boy. Okay, so if you don't want to do a tree diagram, you don't have to. So then you could have boy, 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 girl. Right? That takes care of the situation where the first three are all boys. There's no other possibilities. So now you got to go to, all right, maybe the third kid was a girl, and then it was a boy. The third kid was a girl, and then it was a girl. Again, that's the only possibilities that you could have if the third kid is a girl. Okay? If the second kid was a girl, now we get into more possibilities because I could have boy, boy. Okay? I could have boy, girl. You see what I'm saying? There's a system here. And the tree diagram kind of helps you go through it and find it. So the key thing here is you have to find the total number of possible outcomes first. Because that's going to go on the bottom of your probability. You need to know, okay? Because you guys are not willing to take up the space to write them all down, okay? For every possibility, there are two more possibilities at the next level because there are two boys. There's a boy and a girl. Two possibilities for every child that is born. So what you have to do is keep going with this list until for each one there are two possibilities. The simple answer to the question is to figure out the total number in the sample space. You just have to know how many possibilities there are and how many events there are. There's two possibilities per kid, and there's 4 events because there's 4 kids. That's 2 times 2 times 2 times 2. There are 16 possible outcomes. And if I continued with this list in a systematic way, or if I continued with this tree, at the end you would have 16 different possibilities. So in all of these cases, okay, I'm going to duplicate this real quick. Okay, so what we have to do is look at it this way. These are all out of 16. There's only one way for them to be all girls. Girl, 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 girl. There's one way to do that. So this one's 1 out of 16. That the oldest is a girl. So what you're looking at on your tree diagram is the first one. Well, when I go and I make my tree off of all these, half of my possibilities the first one is a boy, half of my possibilities the first one is a girl. So the oldest is a girl right here. There's 8. There's going to be 8 down here, which is 1/2. Okay, 3 boys. That could be like this. It could be boy, 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 girl. It could be boy, boy, girl, boy. It could be boy, girl, boy, boy. Or it could be girl, boy, boy, boy. Those are the only possibilities that exist where there's 3 boys. That's 4 out of 16 or 1/4. Now, the key thing here that you're struggling with is creating the sample space. Whether you use a tree diagram or a list like I did on the right, I don't care what you use. But you got to make sure that you have the total, okay? And in order to have the total, in order to calculate these different events, you probably want the entire sample space. And yes, does that mean writing out 16 things? Yeah. You have an unlimited supply of paper, okay? Take up the space to do it. If you don't like the tree diagram, don't use it. If you would rather make a table like this, fine, do that. But just remember, for the tree diagram, each event always has the same number of possibilities. And if you want to see the entire, I'll put the tree diagram on the board if you want to see that. You want to, does any of you want to see the whole tree diagram? All right, let me put it up there.